Hello everybody and welcome to Nuclear Physics Lesson 6. Now in the last lesson we spent quite a bit of time doing some derivation of the decay law, but just to remind you of the equations that we looked at, firstly we had A is equal to lambda n, where A is activity and the definition for activity is there on the right hand side. Lambda is the decay constant, and again the definition is there, and n is the number of radioactive nuclei in a given sample. Secondly was the decay law itself. N is equal to n naught e to the minus lambda t, where n naught is the initial number of radioactive nuclei in a large sample. We also then looked that activity will act in a very similar way. A is equal to A naught e to the minus lambda t. And then finally we looked at the equation that linked half-life, T half, and the decay constant, which was T half is natural log of 2 divided by the decay constant. In this lesson then we will be focusing mainly on how to apply these equations to a couple of examples. Firstly though, we're going to have a look at a graphical method of calculating lambda especially, but like I said, mainly we're going to be looking at a couple of examples and hopefully showing you how we can approach problems that we might face from homeworks, exams and stuff like that. Firstly then, let's have a look at a graphical method for calculating anything to do with radioactive decay. As we know from the last couple of videos, we're looking at an exponential decay graph where we have time on the x-axis and we either have number of nuclei or the activity on the y-axis. Now, being a curved graph, that exponential decay graph, it's quite difficult to get anything meaningful out of it without having to draw tangents to the curve, and once we're drawing tangents it does come down to a certain amount of judgment and exactly where a tangent should be and all this kind of stuff. So in physics we do try to avoid that as much as possible and attempt to turn graphs into straight lines wherever we can. So we know from last lesson that if we take it from the number of nuclei point of view, the equation that governs the exponential decay curve that you can see in the top left hand corner is n is equal to n naught e to the minus lambda t, and it is this value here, the blue mark, that gives us n naught. What we want to do with this equation is turn it into a straight line, which means that we need to do something to turn the equation into the format of y is equal to mx plus c. At this point then we need to take that equation and mess around with it and see what we can do with it. So the first thing I'm going to do with this equation is to divide both sides by n naught. So we get n over n naught is equal to e to the minus lambda t. My next step is to take the natural log of both sides. Now natural log of n over n naught is equal to minus lambda t. I won't explain that step there because that step to change natural log of e to the minus lambda t into just minus lambda t was explained in the last video. For the bit on the left hand side of the equation here, we can then rewrite that as natural log of n minus natural log of n naught is equal to minus lambda t. Now that line that I've just written again was part of our derivation of the decay law in the last video. Really we're just unpicking it then to rearrange it. So I'm not going to give too much explanation up to that point because we did the reverse of that step in the Nuclear Decay 5 video. At this point though, what I'm going to do is I'm going to add natural log of n naught to both sides just to move it over to this side of the equation. I'll just change to red so we can see the difference. So natural log of n is equal to minus lambda t plus the natural log of n0. At that stage then we can plot a new graph. On the x-axis we will plot time, and on the y-axis we will plot the natural log of n. If we now compare the equation in red to the general equation of a straight line in green, we can see that, again, I knew where I was going with this obviously, but we've lined everything up with where it should be. The natural log of n is on the y-axis. Time is on the x-axis. What this now shows us is that we expect the gradient of this graph to be minus lambda. What that means is that the gradient of the line will be negative. We can also see that the y-intercept will represent natural log of n0, and we can see that that is also a positive value. Our line will therefore look like this. We will have a positive y-intercept, and that positive y-intercept will be the natural log of n0. We will have a straight line but with a negative gradient. Okay, as straight as I can get it using the pad. But that is now a straight line with a negative gradient. And the gradient of that line represents negative lambda. So gradient will equal minus lambda. In other words, calculate the gradient, which we know will work out as negative, and then if you just remove the negative sign from your calculated gradient, from that you will be able to calculate the decay constant. As a brief interlude before we move on to have a look at the examples that we're going to look at today, I just thought I'd quickly show you which buttons and how we need to use our calculator in order to calculate exponentials and logs. Now the key button is this one here that looks like it says in, but it actually says LN. That stands for natural log. If you just press the button itself, then the calculator will say LN open bracket, and what you will need to do is then put whatever number you are interested in there, and then you will need to close the bracket before you hit equals, or especially if you're doing any other calculations, make sure that you close the bracket. Secondly, if you press shift and then that button, the calculator will give you E and then the box with the cursor on the left hand side. At that point you're now doing E to the power of something, and again you can type your number in there to do E to the power of whatever you're looking for. Just make sure when you are dealing with natural log and with E that you avoid the button immediately to the left of it, which says log and then 10 to the power above. That puts our logs in a different base. It puts it in base 10 rather than in base E, which will give you completely the wrong answer. So always be looking for the button here that I've circled in red, and for the purposes of physics anyway, avoid the button that I've circled in blue. So what we'll move on to now then is to look at a couple of examples of radioactive decay problems similar to the ones that you are going to come across. Now both of these questions are similar to past paper questions. I've taken them and I've adapted them ever so slightly, but the style is going to be very similar. Here's the first one then. A radioactive sample has an activity of 0.5 terabecquerel at a certain time. At this time, an alpha detector showed a count rate of 32 per second. Exactly 10 days later, the count rate had dropped to 8 per second. Find the half-life, decay constant and number of radioactive nuclei present in the sample at the start. How many radioactive nuclei remain 100 days from the start? As usual, pause the video, have a go at this yourself, and then come back when you think you're happy with the answers that you've got. So the first thing we need to do with a question that seems quite long and wordy is we need to pick out some of the relevant information. We also need to have a look at exactly what we're being asked to do. First, let's see what we've been asked to do. Well, we've been asked to find the half-life, so I'm going to call that A. The decay constant I'll call B. The number of radioactive nuclei at the start is C, and then D is how many remain 100 days from the start. So there are 4 different things that we're being asked. We're also given this number here, 0.5 terabecquerel, which is the activity at a certain time. Now what the question is trying to indicate to us is that this is our initial activity A0. Now 0.5 terabecquerel, well, tera is 10 to the 12, so this is telling us 0.5 times 10 to the 12, or we can put that down as 5 times 10 to the 11 becquerel. Now for the first part of this question, to calculate the half-life, it is actually relatively easy. We have an initial count rate of 32 per second, and then we've got a count rate later on of 8 per second. Now, just to sort of point out in this question, we've got an overall activity of 5 times 10 to the 11 becquerels. That's 5 times 10 to the 11 disintegrations, decays per second. This is only pointing at the alpha decay, so this particular sample quite obviously doesn't just give out alpha, it will emit beta and gamma as well, which contributes to that overall 5 times 10 to the 11. So we do need to just make sure that we understand that these things are pointing at 2 completely different ideas. Now I want to look at those numbers and realise that they are far too convenient, and we notice that 32 is obviously 8 times 4, or in other words 8 is a quarter of 32. Because we're dealing with an exponential decay, as soon as we deal with a fraction that has got a power of 2 on the bottom, it's going to work out as a nice number, nice integer number of half-lives. If we have a quarter, we know that that is 2 half-lives. And if you go back 2 videos to Nuclear Physics 4, you'll see the rationale behind that. So therefore 2 half-lives have elapsed, 10 days overall have elapsed, and therefore, nice and easy for A, our half-life is 5 days. Now that we've got the half-life, the next couple of parts should hopefully work themselves out quite well. So that was the answer to A. If we now have a look at B, we're looking now for the decay constant. The best equation to use here is half-life is equal to the natural log of 2 divided by the decay constant. If we rearrange that, the decay constant is natural log of 2 over the half-life. Now natural log of 2, you just put natural log of 2 straight into your calculator. For the half-life it's 5 days, but we do need that half-life in seconds in order to make the units work out properly, so we need to multiply by 24 to get it into hours, 60 to get it into minutes, and 60 to get it into seconds as well. What that then gives us for the decay constant is 1.6 times 10 to the minus 6 per second. The next part, part C, is to work out the number of radioactive nuclei present at the start. So the equation we're going to use here is A0 is equal to lambda N0. That's really just A is equal to lambda N, just with some zeros put on. We are working out N0, which is A0 over lambda. We've calculated lambda in part B. We're given A0 in the question. So we have 5 times 10 to the 11 divided by 1.6 times 10 to the minus 6. and that therefore gives us an answer of 3.1 times 10 to the 17 nuclei. We don't need to bother putting a unit on that because it's a number and is therefore dimensionless. For the last part then, for part D, how many radioactive nuclei remain 100 days from the start? Now there are a couple of different ways of doing this. Firstly, I'll show you the brute force and ignorance way, just by using the decay law itself. N is equal to n naught e to the minus lambda t. Now we've got n naught, that's 3.1 times 10 to the 17, and we can multiply that by e to the power of minus, put this in brackets, 1.6 times 10 to the minus 6 is lambda, that's our decay constant. For the time, we need to multiply it by 100, but as before, we've got to convert that, sorry, we're not multiplying by 5 there, we need to multiply that by 24 and 60 and 60 in order to convert that into seconds. The answer you should get then, if you've used exact calculator answers all the way through this, my calculator tells me that we've got 2.97 times 10 to the 11. I might round that to 2 sig figs like the rest of them, which will give us 3.0 times 10 to the 11 nuclei remaining. Now, as I said, that was the brute force and ignorance method. There is a slightly more elegant method and easier method to get that answer. We've got 100 days, but we know that the half-life is 5 days. So we know, therefore, that we're looking at how many we've got, how many nuclei we've got left after 20 half-lives. Now, if you go back a couple of lessons, we know that that n will be n naught over 2 to the power of the number of half-lives that we're interested in, which will therefore be 2 to the power of 20. Now 2 to the power of 20 is obviously quite a big number, but if you put the numbers into there, so that 3.1 times 10 to the 17 and divide it by 2 to the power of 20, we do end up with 3.0 times 10 to the 11 nuclei as well. So that's just a slightly nicer and slightly more elegant way of working that out. That method will obviously work very well for any number. It doesn't have to be an integer. It's up to you which one you use. I mean, the brute force and ignorance way is probably the better way of doing it if you aren't confident with doing it using powers of 2 and all that kind of stuff. So if you're not confident, I would go for the n equals n naught e to the minus lambda t. If you are really confident, then you can have a go at using your powers of 2 there. For the second example then, we're going to have a look at, again, a very typical question, which is obviously very different to the one we've seen before, but it's definitely along the line of the style that you're going to get from exam boards. So have a read of the question. It's quite long, so I'm not going to read this one out. I'm going to trust you lot to be able to read. Have a go at it, and again, come back when you think you've got an answer that you're happy with. So on the face of it, this seems like quite a complicated question, but in a moment you'll see that once we understand what it's trying to ask us, we will easily be able to work out the answer, and it's very simple. We're not even going to have to touch our calculators for this example at all. This here is an extremely important line. No atoms escaped from the sample. Now what that means is that for every potassium-40 atom that has decayed, it is now either calcium or argon. Nothing has come in, nothing has gone out. We've got the same number of atoms overall. So when we look at that then, the total number of atoms that we have in this grid here is 3 times 10 to the 12 plus 8 times 10 to the 12 plus 1 times 10 to the 12. That gives us 12 times 10 to the 12. Now I know that strictly that's not exactly how we should write standard form, I'm aware of that, but you'll see why I'm trying to make this point in a moment. Now by working this out, we've actually already now worked out the answer to this bit here, so calculate the number that was present when the rock was originally formed, and it is this number here, 12 times 10 to the 12. If I was writing that as an exam answer, I would then write that as 1.2 times 10 to the 13, just to make it nice and neat and show that we do know what we're doing and can give our answers properly, but we will be using that 12 times 10 to the 12 in a moment. Now for the second part, to calculate how old the rock is for this section here. If the initial number was 12 times 10 to the 12, so that would be n0. This number here, 3 times 10 to the 12, is n. What we can now see is that n over n0 is a quarter. In other words, we have got a quarter of the initial value, a quarter of the initial number of nuclei that we had in the sample. Once again, we've ended up with a nice fraction with a power of 2 at the bottom. What that's trying to tell us then is that 2 half-lives have elapsed in order to give us the situation that we see up here. We're given the half-life 1.3 times 10 to the 9 years, and therefore we simply multiply that by 2. 2.6 times 10 to the 9 years is the age of the rock. So to summarise the lesson then, the main new bit of theory that we've done today is to say that if we do a graph of natural log of n against t, that the gradient of that graph will give us the negative of the decay constant, and that the y-intercept will be natural log of n0. Obviously then we went on to have a look at a couple of different examples. As usual, if you've got any questions on that, please let one of us know, and I'll see you next lesson.